Good morning, everyone. Today, I'm pleased to present an in-depth study and analysis of industrial furnaces, focusing on continuous processes engineering applied thermodynamics, and in particular, heat transfer phenomena and phasing design. The objective of this presentation is to explain how the equipment transfers thermal energy to process raw materials on a large scale, and how engineers must calculate, standardize, and optimize this system to achieve sustainable operation in modern industry. Let's begin with a brief but necessary historical overview. The evolution of industrial heating is intrinsically linked to humanity's technological development. In the pre-industrial era, kilns were rudimentary, intermittent structures commonly built of clay or stone, where fuels such as wood or charcoal was burned in the same space as the carbon, drastically limiting temperature control. With the advent of the Industrial Revolution in the 19th century, the introduction of coal and the design of separate combustion chambers marked the first major milestone in efficiency. However, the true quantum leap occurred in the 20th century thanks to conveyor belt automation and the advent of natural gas and electricity. This enabled the transition from batch processes to continuous production lines. Today, the trend is Industry 4.0, modular, multi-zone systems controlled by PID algorithms and real-time sensors that optimize critical variables such as residence time and thermal uniformity. To approach an oven from a thermal engineering perspective, the first essential step is to define it in terms of the principles of thermodynamics. We model the furnace as a steady state control volume, applying the first law of the thermodynamics for open systems. The fundamental equation for energy conservation states that the energy entering the system must be exactly equal to energy leaving it. In this model, the incoming heat flow comes primarily from the false calorific value for the electrical power of the heating elements. This energy is divided into three components. First, the useful heat absorbed by the load, referred to as Q load. Second, the sensible heat carried away by the exhaust gases through the chimney. And third, the inevitable heat loss through the walls. Our job as designers is to maximize payload capacity and minimize losses. Inside the chamber, energy interacts through three fundamental mechanisms of heat transfer: radiation, convection, and conduction. Radiation is the primary mechanism when operating at high temperatures, typically above 700 degrees Celsius. Convection helps to even out the temperature of the internal atmosphere, allowing hot gases to surround the product. Finally, conduction carries heat toward the center of the load, but it also causes heat loss through the insulation into surrounding environment. Let's take a closer look at the physics of radiation. Recall Stefan Boltzmann law expressed by the physical formula shown on the screen. These exponential relationships explain why radiation accounts for between 18 and 19% of total heat transfer. Convective heat transfer is governed by Newton's law of cooling, in which the coefficient H is the K variable. In continuous ovens, we must calculate the residence time to prevent the product from becoming burned on the outside but raw on the inside. Let's take a look at our case study, the continuous belt dryer for corn shown in this file photo. It features On outer frame made is AISI 304 stainless steel, chosen for its high corrosion resistance and ease of cleaning. The design is modular, allowing for the configuration of a zone temperature profile along the entire path for the various stages of dehydration and roasting. The product moves along an interwoven metal mesh belt, which has a high open area radio to facilitate the transfer. A critical feature is the mechanical tensors that compensate for the thermal expansion of the metal strip as it enters the high temperature chamber. At the top, the pyramid shape exhaust hoods remove the combustion gases and water vapor released by the core. Using a heat recovery system, the waste heat from the flue gases is used to preheat the combustion air, resulting in significant savings. In conclusion, the design of an industrial furnaces represents a perfect balance between thermodynamics, fluid mechanics, and material science. I sincerely appreciate your attention. Please feel free to contact me if you have any questions. Thank you so much.